Here we go again, ladies and gentlemen. This is the next section, 2.4. This deals with what we call the remainder and the factor theorem. Now, what you're understanding, hopefully, is that when you divide this polynomials, when you divide a polynomial by a binomial, whatever, you're reducing it, right? It's like dividing a quadratic. Let's look at something that we understand. If I divide this by x plus 3, I can see that this is x plus 3 times x plus 2. So if I divide it by x plus 3, that's going to equal x plus 2, which means that x plus 3 times x plus 2 is equal to x squared plus 5x plus 6, right? So we can go round and around and around here. Let me see if I turn that light off, it makes it any better. Man, it's a little bit better. We can go round and around, and we look at equivalencies, and we can see how we can break a polynomial up by dividing it into two sections, sometimes three sections. Or factors. We've been dealing mostly with quadratics in grade 11, and a lot right now. We use it as an example. That breaks down into two factors. A cubic potentially breaks down into three factors, right? Quartic breaks down into potentially four factors, right? So here's a cubic, breaks down into potentially three factors. It all determines on how many times it crosses the x-axis, right? So, the remainder theorem, okay? When we're doing this long division, we find the remainder. The remainder doesn't really tell us much. What we're looking for specifically is a remainder of 0, right? Because if you divide something evenly, if you divide 3 into 12 and you get 4 with the remainder of 0, when you have a remainder of 0, it means that this divisor is a factor of your dividend, okay? The divisor times the quotient is equal to the dividend. Now, I've given you this statement before. It's in your textbook already. Just know what the hell I'm talking about when I use divisor, dividend, and quotient, okay? So the remainder theorem, what we're looking for is that remainder of 0, okay? So we don't have to go through long division. The remainder theorem states simply this, that if a polynomial in x, that means p of x, okay? We can describe it as p of x. If p of x is divided by x minus a, then pa is what they call the remainder. So let's look at a polynomial here. Let's go 2x to the power of 4 minus 3x cubed plus 2x minus 3. We're going to divide this by x minus 2. Now you can go through the whole long division process. You can do synthetic division if you'd like to find the remainder. But when you do that, you also get the quotient. I don't really want the quotient yet. I don't want to find the quotient until I know that my remainder is going to be 0, because I'm wasting my time. So what we do is this this remainder theorem. So x minus a, that means that x is equal to 2. So that means that so this is my p of x, right? So p of 2 will be what? That'll be 2 times 2 to the power of 4 minus 3 times 2 to the power of 3 plus 2 times 2 minus 3. 2 to the power of 4, 16, 2, 4, 8. So this is 16, so that becomes 32. That's 8 minus 24 plus 4 minus 3. That gives me, let's look, 36 minus 20. That gives me a remainder of 9. So that means that x minus 2 is not a factor. Okay? I don't get a remainder of 0, but I find my remainder of 9. Now you could verify this if you like using synthetic or long division, or you can simply take my word for it. Okay? Let's look at a more complicated one potentially. If I said x to the power of 17, where am I? Minus 2x to the power of 12 plus 7, if that's divided by x plus 1, what do we do? Well, what I do is I say, okay, if this is my polynomial in x, right? Well, my polynomial in here, x is equal to negative 1. So negative 1 will be negative 1 to the power of 17 minus 2 times negative 1 to the power of 12 plus 7. That will give me negative 1. That will give me negative 2. That will give me 7. That gives me 5. I have a remainder of 5. Again, you could verify this using synthetic division or long division. I I'm going to continue with the next topic here, okay? So, what do we got next? Find the remainder, and oh, look, I just did that question. Isn't that funny? Shows you how organized I am. So maybe you can give this a shot again now. It's the same question I did before. Anyways, now, the next thing I want to look at is this thing called the factor theorem. And the factor theorem is a direct result of the remainder theorem, okay? It basically states that if you do this up here, and you find a remainder of 0, it means that it is indeed a factor, okay? So if p of x is divided by x minus a, again, let's go x minus a here, and p of a equals 0, then it means that x minus a is a factor of p of x, okay? And it means that a is a solution as well, okay? And a is a solution or a root or a 0 or an x-intercept, all right? Now, I am going to give you an example right now. Let's have a look. Hold on a sec, just give me a sec here, guys. I'll get organized. Okay, so I have a polynomial in x, and that's equal to 3x to the power of 4 plus 4x cubed minus 3x squared minus 3x minus 10. And I'm going to divide that by x plus 2. Okay, now I'm asking you, is this a factor of that polynomial? Well, let's check it out. So that means that your polynomial in -2 is going to be 3 times. -2 to the power of 4 is positive 16. Okay, plus 4 times -2 to the power of 3 is -8. Minus 3 times -2 squared is 4. Minus 3 times -2, which is just -2 minus 10. So this is 30 and 18, 48. This is minus 32. This is minus 12. That's plus 6. That's minus 10. So this is 48 minus 44. That's 4 plus 6 minus 10. This does indeed equal 0. Okay? So the idea is that now you know that this is a factor. Okay, so now the idea would be to do the long division. Okay, do the long division. Find out what your cubic is, and then work from there. Okay, but right now what we're trying to just figure out is this theorem. Okay, so if you plug in the x value, your solution, if you plug in the potential solution here into your x value, if you get a remainder of 0, it means that this is a factor and this is a solution. That means that is one of the x-intercepts, okay, at -2. All right, so now I'm going to go to this next one because there's a couple things here that are a little bit weird, not weird, okay, but what I need you to think about here is if you have, let's look at x squared plus 7x plus 10, okay? When you break this down, you know that this front, because that's a 1, this has to be an x and an x, because there's no other numbers that can multiply to give you a 1 here, and x give you x squared. Now you know that these numbers here have to be a 5 and a 2, or they have to be a 10 and a 1, right? Plus or minus, plus or minus, plus or minus, plus or minus. So what we're looking at are all the possible combinations that can give you this last number. Now, this doesn't change if you get into higher degree polynomials, okay? If I have an x cubed plus 7x squared minus 5x plus 1, this is going to have at least one solution. And I can tell you, well, let's make this a 10 here. And I can tell you that it potentially has 3 factors, potentially. If it crosses 3 times, it has 3 solutions. It can cross twice and have 2 solutions. It can cross once or bounce or whatever and have 1 solution, okay? Now understand a cubic has to have at least 1 solution and a maximum of 3. We're going to assume it has all 3. But what we do know, since this is a 1 here, that this has to be an x and an x and an x. There's nothing else that can go on, right? So we also look at the last numbers. All these numbers have to multiply to give you 10. So they all have to be factors of 10. Now, this gets a little bit more complicated. Let's look at this here. Now, let's make another comparison here. Let's look at 2x squared plus, oh, hold on, give me a sec, 2x plus 1 and x minus 3. 2x minus 5x minus 3. Now we're going to break this down. We see that this has to be 2x and x because they have to multiply. Now it could be x and 2, could be that. Now this has to be a 1 and 3, or what else could it be? It could be 2x and a 3, and an x and a 1, and it could be a plus or minus, it could be a plus or minus, it could be a plus or minus, it could be a plus or minus. We're looking at more options, right? These are both prime numbers, though. What happens if we end up having something like this? How about let's go 3x squared plus, I don't even care what it is, and let's go plus 8 here, okay? Well, now what our choices are, well, this can be a 3x, this has to be an x, or it could be an x and a 3. It doesn't really matter, right? Let's just flip the other ones. Now, this has to be factors of 8, so it's a 1 and an 8. Well, what's another possibility? How about an 8 and a 1? That's another possibility. How about 3x and 2 and x and 4? Or how about, sorry here, 3x, how about we go 3x and the 4 on this side and the 2 on this side. Now remember, we know that we can probably factor this, okay? But what we're just looking at are all the potential and only plausible solutions. So this is it, right? There's no other factors of 8. There's nothing else that will multiply to give you 8, and there's nothing else that would multiply to give you 3x. So if you made a solution for every single one of these, this, right? If this was a factor, your solution would be plus or minus 1/3. And here it would be plus or minus 8. In this case, it's going to be plus or minus 8/3. And in this case, it's plus or minus 1. In this case, it's plus or minus 2/3. And in this case, it's plus or minus 4. In this case, it's plus or minus 4/3. And in this case, it's plus or minus 2. Now, if you don't know where these ones came, let me quickly show you. If you don't know how to find the solution, let's take this one. If 3x plus 1 is equal to 0, you just solve it for, because that's what it is, right? If there's solutions, then it equals 0. So then you just solve for x. 3x equals negative 1, x equals negative 1/3. That's where these come from. So this is something that we're going to now apply to higher degree polynomials. And notice that it looks at the last and the first numbers, the constant and the leading coefficient. And if you can make some sort of connection here, it's basically all the combinations of this over the factors of 8 over the factors of 3. And I'm just going to show you this theorem right now and then give you an example. And that's going to be a pretty long video. So hopefully that made a little bit of sense. I'll go over it in class. So it looks at leading coefficient and constant, right? That's what we're talking about here. It's looking at the leading coefficient and the constant. If a polynomial x, p of x, has integer coefficients, that means they're a positive or a negative number, that every rational solution of p of x, because they're irrational, you're going to be using things like the quadratic formula. Every rational solution of p of x is in the form b of a, where b is all the factors of the constant. So that 1, so all the factors of that constant that we were looking at, for example, 8, all the factors of 8 are 1, 2, 4, and 8, right? And over the leading, or the factors of the leading coefficient, so 3 here. So 1 and 3 are the only factors of that, all right? Now, I will just give you one quick example because this can be a little bit funky. Okay, but let's look at a polynomial p of x. All right, we have p of x, and it is given as x cubed minus 9x squared plus 20x minus 12. So identify your a. This is your a. So what's your a? There's a 1 here, right? So a is 1 and b is negative 12. So a, so if I put all my b's over a's, right, because it says all your b's over a's. So you take plus or minus 1, plus or minus 2, plus or minus 3, plus or minus 4, plus or minus 6, plus or minus 12. Those are all the factors of 12. Now, what are all the factors of a? Well, that's just plus or minus 1. So again, when you have that leading coefficient of 1, it becomes pretty darn easy, right? Because it's just all the factors of those. So what you can say here is that your possible solutions are plus or minus 1, plus or minus 2, plus or minus 3, plus or minus 4, plus or minus 6, and plus or minus 12. And what you're going to have to do is start plugging them in. So you plug in P of 1, P of -2, P of -2, and keep going until, guess what? Until you find a remainder of 0. Okay? Now, I'm going to let you guys work on that, and we're going to deal with it in class. It's been a long video so far, and I apologize for that, but this is a pretty funky concept. I just want to give you one more example here where we're not going to have a leading coefficient of 1. Okay? So P of x is equal to 4x cubed plus 12x squared plus 5x minus 6. Now, look at all your factors here. So b, let's look, anyways, this is your b, this is your a, right? So all your b over a's. Now, your b, plus or minus 1, plus or minus 2, plus or minus 3, plus or minus 6. Those are all the factors of 6. Now 4, plus or minus 1, plus or minus 4. And every single combination. So your possible solutions. Okay, now 1 over 1 is just 1. 2 over 1 is just 2. 3 over 1 is just 3. Oops, and I'm an idiot. And plus or minus 2 on the bottom here. My apologies. And then 6 over 1 is plus or minus 6. Now, let's go 2, 4. 2 over 4, well, that's 1/2, right? And then 3 over 4. And then 6 over 4, which is 3/2. And then we go here. 1 over 2 is 1/2. Already got it. 2 over 2 is 1. Already got it. 3 over 2 is already got it. 6 over 2 is 3. Already got it. So these are all your probable solutions, and what you're going to have to start doing is plugging them in. And I would suggest starting with the easy ones first, okay? Ladies and gentlemen, thank you very much for your time. Hopefully it made a little bit of sense, and we'll sort out any issues you have.